Okay, so good morning, everyone. So I'm a Yuntao, I'm a postdoc currently at UCLA at Hongzhou's lab at California National System Institute. And today I'm very grateful to that I can come here to tell you about our recent our software development for the using deep learning to restore the missing information in the cryo-electron tomography. So the title is Isotropic Reconstruction for electron tomography with deep learning. So this is we have a software that deal with this problem. So the so now we'll start from the cryo-electron tomography and from yesterday's lectures. I would know the concept of the cryo-electron tomography and the con it is the sample it has should be embedded in a thin slice of ice. And if you want to image it to 3D, you need to tilt the sample to a different tilt angle. So typically with a step of 2 or 3, and the maximum tilt angle is probably 60. So this tilted scheme, and after you collect image, you do the weighted back projection using the reconstruction software such as iMod to obtain the 3D. So this is what the process should look like. And you probably noticed that in the weighted back projection, it's not in covered all the angle from -90 to +90. It's only covered to 60 to plus -60 to +60. So it leading to information loss. That loss is actually in the Fourier space called it looks like a wedge, so called missing wedge. So it's missing information cause artifacts. And the second one is a low signal to noise ratio because the limited dosage should be distributed on the maybe 41 or 61 images. So the tomogram suffers a low signal to noise ratio problem. So it's getting more difficult to for us to to make a good looking cryo-electron tomogram. So to This is an example of the missing wedge problem, the cryo-electron in the cryotomogram. So if, for example, this is original image, this is the Einstein image. If you tilt the sample with 5 degree increment, and from the first one is covers the entire 180 degree, and gradually you remove the data at high tilt and to the -50, you find the image is actually at the beginning the Einstein phase you can recognize, and after you have them after apply the missing wedge, you, it's very difficult to recognize the Einstein's phase. So this is a typical situation in a cryo-ET. You cannot identify the what you are looking for on the z-axis. So this causes elongation of the particle you have. So this is artifact that we have been suffering for decades since the invention of cryo-EM or even the electron tomography. So this is a real example. This is what have been working on. It's a neuron synapse. So it's an inhibitory synapse. So we can see in the XY plane it looks fine. You can see the vesicles fusing with membrane and have something on the postsynaptic membrane. Looks like as a protein size. So we can do the subtotal averaging to fill the missing information, and we can do the reconstruction of the semi-identical protein. But if you see the overall structure, the membranes, to see the x and z axis or y z axis is not very as good as the xy plane. So you can see the vesicle are not actually spherical in this plane. And can see the bingo beam is it have a very long tail, it elongated along the axis. This is what have been suffering for a lot, and because those kind of organelles we want to see, and but cannot be averaged. So yes, probably want to get rid of it. So when I look at this, I I I found I I write a formula. So this is so how this missing wedge come from? So so if we have the observed tomogram with the node as y, and we have a ground truth, and if you have a ground truth that covers the entire Fourier space, and this is a missing wedge mask, if you multiply the missing wedge mask to the ground truth in the Fourier space, we get observed tomogram. So this is the same with if you have a full coverage of the data, and you apply the mask look like this, look like a wedge, to get the original tomogram. So this, so isoNet, so which is what the software I'm working on, is the target is to solve this equation. So you know the y, you know the missing wedge, but you want to solve for the ground truth, which is x. So we're working for well we wanted. So this is so wanted to get. So if you want to have a training algorithm that maps y to x, which is fine, but the problem is there's no ground truth for neural net training. So you have a neural net training to recover the missing information, and cannot. It's difficult to get the data. The second one is if you want to do the AI, the AI generate images. AI generate image is now everywhere you can search a lot. So it's AI generate information, but that information may not be trustworthy. Sometimes ChatGPT generates some random words and looks nice, but actually does not make sense. So AI generated information may not be trustworthy in terms of this generative model. So what we have think about is we don't rely on the ground truth. We don't rely on the external information. What this is a strategy of our isoNet. So the key point is to make the data as trustworthy as possible. What the strategy is? So to recover the missing information, we have this 5 step. Okay, so you know the deep learning need a ground truth, and we do this have the first step to assume that our observed data is ground truth. Assume that our one tomogram is ground truth, and then we remove some information from ground truth. This is happening in silico. So you remove information from ground truth, and then we pretend we don't know that information. So then we can train the network to predict missing information that would manually remove in silico from the remaining data. So I have ground truth and remove information from ground truth, and then train the network from the removed information tomogram to the so-called ground truth tomogram. So this we can train. So this is no problem we have trained. So everything is self-supervised. So network is trained on your data and predict on your own data. The only problem is the ground truth is no longer the real ground truth, but you manipulate this is the data you have. So when you after we train the network, use the train network to improve the ground truth. So that goes with 5 steps. So assume that data is ground truth and train the network and improve the ground truth with the network and go back to the step 1. So it relies on iterative training of the from the data. So this is how the iteration works. So we have a so for example we have a tomogram. We crop subtomogram from the tomograms. So first one we get some we made the rotation, so it rotates the subtomogram. So for example in this case 90-degree rotation. So if you rotate the subtomogram, it's no longer has a missing wedge as the axis, and we can then apply another missing wedge. This is applying missing wedge is in silico remove information from the data. So apply another missing wedge. So this subtomogram have two missing wedge. Okay, so this subtomogram has one missing wedge. And this from this two data set, two X and Y, and then we can train the data. So we have X with in silico remove information. Y is the one that is already rotated subtomogram, and then we can train it with a neural network. So then we have data to train the neural network. And after training, we update the neural network, and we have put the original subtomogram, and it output the corrected subtomogram. This is one step, but this during the training, the ground truth is not actually ground truth. So we use a corrected tomogram and add it back to the original subtomogram. So this one added to the original subtomogram, and then the added back information, so it looks better. So every time it looks a little bit better for the filling the information. So then we can do the preparation again. So each iteration, we have basically optimized the neural network, and then we have a option operation to optimize the training data. So there is a so that every iteration trains the network to from the tomo data in this iteration. And during the refine step, we have a noise to noise denoising. So basically, you add noise to training data. You ask the network to remove the noise from the remove the added noise with the neural network. So the isoNet itself has a denoising strategy that helps the tomogram to get rid of noise, because the noise is a very very important aspect, very difficult to handle in the cryo-ET. So the neural network we determine use is called the UNet. UNet is this is a fully convolutional. So it have in each step it have a 3x3 convolution, and with an activation function. So this is a three step of convolution. And the good thing for the UNet is it trains the neural network not only in the original resolution, but also have the downsampling layer. Downsampling layer to makes the neural network train with a lower resolution. So after at 1, 2, 3, three steps of downsampling, you can train the data with lower information, so it covers many different range of Fourier space. This is why the UNet is successful, because you have the downsampling and consider all the resolution range. So this is a neural network we are using. And we tested on simulated data. This is apoferritin. We generate 10 subtomogram of apoferritin and manually apply the missing wedge. So as you know, the isoNet requires our software isoNet requires the iterative removal of the iterative removal and recovery in the missing wedge. So at the iteration 0, it looks like this has a hole on top and bottom. This is typical. If you observe the cryo-ET tomogram, it looks like it has a hole on it. And gradually through the iteration, so the iteration includes the simulated, so apply another missing wedge and train the network from the simulated applied missing wedge subtomogram to the not non-applied. So this after iteration 1, 2, 3, 4, 5. So gradually the density become more prominent, so more continuous. So the alpha helix, the simulated data has alpha helix. So alpha helix you can see is almost identical in the different orientation. So this is apoferritin. We didn't use the symmetry of the apoferritin, but merely let the apoferritin data set go through each iteration. This is simulated data. And then we move on to real data. The real data is first data set we have been trying is immature HIV. So this data set comes from the John Brice group, which is a very standard data set to for the test the algorithm. So the so the so this data set have HIV virus-like particle. So if you see it in the tomogram, it has this kind of spherical shape, and have the GAG protein, and has to form this so-called the immature capsid. So if you do the I mode with weighted back projection, the first thing you can see is very noisy, and then you can see the artifacts. So it has a striking effect, and also the missing on the top and bottom of the capsid. So this is a IMO with weighted back projection. And if you do the Fourier transform, the Fourier space will look like this. Has the wedge-shaped missing region. So this region is devoid of information. So but if you do the isoNet CTF deconvolution, so CTF deconvolution is just to divide the CTF by to correct the CTF by window filter. So the window filter application, the typically upscale the low resolution information, so you can see the contrast is better than the iMod. So this CTF deconvolution is similar with what CTF deconvolution in the WAP. So, but it's actually improved the contrast, so people can see things. But it's still not enough because the GAG protein are not clearly visible here, and also on the top and bottom of the surface. So it should be spherical. It should have an enclosed virus capsid. And with the isoNet missing wedge correction module, so we have a you can see the HIV original is not complete. Now it looks like it's almost complete. And for the gold beads, the gold bead is very clear. The previously is have the X shape, and after the correction, it's become spherical. So this is isoNet missing wedge correction, and this is a cryo-ET. So cryo-ET typically people don't show the 3D directly show the cryo-EM density, because if you see the z-axis will be artifact. But after isoNet, you can directly show the 3D. This is without any density cryo-EM density modification. This is only just show the raw density after the correction. And beyond that, we look carefully at the as a GAG protein lattice, you can see some imperfect defect of the lattice, because if the HIV only formed by the hexamer, so it cannot be a spherical. So it should have some defect, so it makes it spherical. So we observe, each edge, all the edge of the HIV has this kind of protrusion. So this indicates the GAG protein has a building block of dimer, not hexamer. So it's this small density here just confirm that the dimer has its building block. So it's not assembled by each individual the hexagonal pattern. So this is consistent. After we get this data, we find the paper that publishes has so do the subtotal averaging. So this conclusion is the same with what they're averaging. So that means isoNet can trustworthy fill the missing information trustworthy, and it matches what the subtotal average shows. So we have so from the virus we go to the organelle, so to test our software. So this is the flagella from the organism called the Trypanosome brucei. So this is the structure of the axonine. So axonine has a microtubule doublet, and also has a dining, and also the radial spoke. So this is a IMO reconstruction. If you see the z-axis, x-axis, you can see the artifact along that. And after doing an isoNet correction, so you can clearly see the doublet structure. If you compare the IMO, it's kind of it's a lot different. and this is actually what it should look like. Also, beyond the axon, you can see the pattern structure of the paraflagellar rod. So this is additional density that people haven't been described. So at that time, so you can clearly see the pattern of the additional cryo-ET density. And you can also notice that denoising actually helps because the original data has a very noisy, and after isoNet treatment, the noiser to noise strategy actually helps to visualize the microtubule, the outer arm dining. This is the first flagella, and then from the organelle, we'll move on to the another to the cell sample. So what we're testing is a data set from the neuron. So they will capture the neuron on the grid, so on the ghost grid. So the neuron in the bright field microscopy looks like this. It's a cell body, has a lot of neurites called axon and dendrite that covers the entire grid. And we'll go to the very far from the cell body area and to take the tomogram of the synapses. So this is the eye mode reconstruction of the synapse, and this is you can see that this is a presynaptic bottom, and this is a postsynaptic counterpart. So have a have a gap between them, and it has a postsynaptic density. It's very difficult to observe the postsynaptic density in cryo-EM, and but it is there. And we have the vesicle, a lot of vesicle and the microtubules in the presynaptic. And if you look at z-axis, it's very noisy and have a irregular shape of the vesicle. It should be spherical. May not be ideally spherical, but should be most of them should be similar in the x and y, x, y, z axis. This is the artifact caused by the eye modification. But if you do the isoNet treatment, this is the first one is denoising, and second one you can see the vesicle are all complete. So it's a complete the complete spherical. So if you compare that, you can see that this kind of black dot. So this black dot actually the top membrane or the bottom membrane of the vesicle. If you don't have the isoNet crusher, you never see this top and bottom. So this is the first one. After this tomogram we found those are kind of weird. So it's how they can get the black spots. So it turned out to be after the correction, the top surface and bottom surface of the vesicle comes back. So this is the effect of missing wedge correction. But anyway, we have also another thing, a lot of small dots. Those small dots are actually the small proteins. If you previously cannot even clearly recognize after the isoNet correction, this kind of dots appear. So you can see on the z-axis a lot of the small proteins, also in the both in the pre and post synaptic part, are become quite visible. So it can be quantified. So only after the isoNet. This is a detailed comparison. This is the IMOD reconstruction, and this is IMOD reconstruction is the input of the isoNet. So this is the input isoNet, the output of isoNet. So you can see very clearly these dots are the protein that exists before isoNet, but become more clear. Also, the linker between the vesicles can much easier to see in the x-axis. Also, the microtubule is cut at an angle, so you can see the small patch. So this one is a small dot. It's the filament, the single subunit of the tubulin alpha and beta. So before the isoNet correction, it's just empty. So this is how isoNet corrects the missing information from tomogram of the neuron. So we're going to next one. It's also the neurons, the different synapses. We observe this kind of very interesting structures. So it has a hexagon shape, and also sometimes it has a pentagon shape. So this is called clustering cage. So clustering is a can assemble as a cage that can be used for endocytosis of the vesicle. So the so it can very useful for the vesicle recycling because the neuron relies on a lot of vesicle recycling for the neurotransmitter release. So this is IMO reconstruction, and it looks okay on XY axis, XY plane. But if you see the Z plane, it can become very smear. Also, also it's very hard to recognize this kind of pentagon or hexagon lattice. And after doing the isoNet, it's just on the z-axis, it is much more clear. And also this kind of uh pentagon shape this is here, and compare it, it is very difficult to recognize. But it is there, but it cannot very easier to recognize by. So this is the effect in the another tomogram of synapse. We can do the manual tracing of the clustering cage. So the clustering cage. So I have can manual tracing and count the number of hexagon and pentagon on the cage. And this is a result. Different color means different type of the type of cage. So the this one is this one is the in vitro single particle analysis of purified X clustering structure. So what they observed that the mini code, the sweet potato, different geometry, but those geometry are in vitro sample, so it may not represent the true structure inside the cell. So and in the isoNet, we don't do any averaging. So this is we can see the isoNet can create some data that almost almost comparable to the structure after the cryo-EM averaging. So so this is a z-axis and x-axis and xy-axis. So it it looks like the artifact, the missing white artifact is just a lot of them are just be recovered. So this is a individual cage, and this is a mini code which is corresponding to this mini code. And finally, we can see one very large uh, clustering cage has a heptagon. So it has one, two, three, four, five, six, seven. So it has 7 vertices. So without the isoNet, it's very difficult to see the structure. And if you want to do the template matching or if you do the subtotal averaging to classify, it's kind of difficult to capture the single instance that has the 7 vertices on the cage. So this is a beauty of seeing the structure without averaging, just observe as a whole without just pick the particle. So we can discover the heptagon ball with directly observe it. So this is what we demonstrate how we demonstrate the isoNet works for the neuron data set. So this one is a GUI for the isoNet. So we have a so this is I think based on what I guess from other people is kind of difficult easy to use, and typically you want to use insert to add tomogram. So this is the GUI of the isoNet. You can click the insert, add the one tomogram and type the pixel size, the focus, and relevant parameter for each tomogram. And then, so this tomogram should be bin. So because the neural network training is kind of sensitive to binning, so sometimes using the bin 4, bin 8 to get a pixel size around 10 angstrom. This is typical what we do is the 10 angstrom. pixel size of tomogram was kind of the best. And if you target on smaller proteins, probably want to have a small pixel size. Um, then we have few different functionality. One is the CTF deconvolution, which I already talked about, so improve the contrast, and also the alpha mitigate the CTF artifact and generate mask. So the mask generation is to avoid the place that is empty, because if you're empty, if you're trained with a neural network, it's still empty. So that means you wasted time on doing that, and it makes the training less efficient, and to avoid any empty area, carbon area, and platinum area. So if you have a layer of higher contrast platinum, and then we have a extract, we have a subtomogram extraction. So subtomogram extraction is for prepare neural data for prepare subtotal data for the neural network training. So this is the three additional functionality. The actual iterative training happening in this tab, which is a refinement. It actually only just you can just click once. I will give you a neural network without manually go through the iteration. And then the final one is a prediction. Prediction is basically just apply the neural network to tomogram. So apply the neural network to tomogram to crack the missing information in the tomogram. Because in the training you work on subtomogram, and after training you use the network to apply for entire tomogram. This is a workflow of the isoNet we have. And in the next part, I want to briefly introduce another concept we have. We call single particle isoNet. So we call spIsoNet. So this spIsoNet is just published few months ago, and you can search for that the in the Google Scholar and other platforms. So this one is beyond the isoNet. You can use the information recovery ability to help the cryo-EM single particle analysis and subtomogram averaging. It helps a lot for the single particle and also the averaging part for the using the ability to cover information, because we can think of isoNet. It can give you information without external treatment. So it has a reconstruction algorithm that provides you information for free. And this is a primary problem we are going to target for the spIsoNet. spIsoNet is primarily target on preferred orientation problem. So preferred orientation problem is because if you put the single particle say sample or on the grid, it typically goes to the air-water interface. So either go to so probably this is an example that the tomogram of recovered by isoNet. You can see the ribosome, almost all of them goes to the carbon-water interface or air-water interface. This causes a problem because the particle tends to stick to the interfaces with particular orientation. So it causes the preferred orientation. So it is a single most important problem if you haven't got a very good structure from the single particle, in the 30% of probability you get preferred orientation problem. So basically, preferred orientation problem is another problem similar to the missing wedge, that you have missing some information from some of the views. This is an example. So this is from other people's data. So we have an angular distribution with a strong preferred orientation with only two views right there. And if you do the reconstruction, the FSC looks fine. So it looks like I have a 3.6 angstrom, but as one view it looks good. But on the other view, which we probably see is the z axis, it becomes elongated. So this is This is a problem caused by the prefer orientation induced artifact, and which is also similar with the missing wedge induced artifact. Then we developed a single particle isoNet for doing that. So this is a special design. We use a three-dimensional Fourier shell correlation to represent how in the prefer orientation just to tells you where the tomogram in the single particle reconstruction has the missing information in the Fourier space. And this is end-to-end training. So because if you see the isoNet, it has the iterations. For this one, single particle isoNet, it does not have to go through iterations end-to-end. And also we have implement the noise to noise instead of the noise to noise in the isoNet, noise to noise in noise. And can have a spIsoNet regularization, which for the particle alignment. This is similar with the concept as a flush regularization. You put the neural network in between the particle alignment, so it helps the particle alignment. So, but the has shared property with the cryo-tomogram isoNet. Only learn from experimental data. There's no external information provided, so it becomes more trustworthy than the other algorithm that modify your density through the training from protein data. So this one, single particle isoNet, only use your experimental data set. These are the two modules. One is an anisotropy reconstruction. Is design the complex network for the. So the purpose of this is doing two things. One thing is doing the information recovery. This is this is with distortion. This is distortion corrected. This is with a missing cone. And then another purpose is doing the noise to noise training. So the remove the noise from the cryo-EM structure. So the input of an anisotropy question is the half map 1 and 2, and probably want to give it a mask to tell them where should be your data, where should be your structure. And another module is a misalignment question, which takes a particle data set and tends to help with a better particle alignment. So this is the first module. This is an anisotropy question. I have a 4 losses, so it goes from beginning to the end. So everything in the training, so don't rely on the iteration. So this generate data and rotate and filter and do the network prediction are embedded inside this training process. And we designed the 4 losses, actually 3 kind of losses. One is a consistency loss. It's a consistency loss, equivariance loss, and noise to noise loss. So consistent loss is guide to the recovery to the undersample Fourier regions. So you have the Fourier space, is the recovery should only appear in the undersample Fourier region, will not modify the well-represented regions. So equivariance loss is to learn the information and learn from the remove information in the rotated map. So the equivariance loss is what we designed for the isoNet. Actually the learning happens. And noise to noise loss is trying to use a pair of input to denoise. So they have 3 losses. Consistent loss is ensure it only happen in the Fourier sample region, on the sample region, and the equivariance loss actually recover the information. The 3 losses. So if you balance them, it gets a distortion correction. So this is a performance. So if you do the missing cone, this is a 45-degree missing cone. It's a before correction and after correction. And this is 60-degree. So actually the 60-degree missing. So the 30-degree remaining missing cone. And this is the before and after. This is only 15 angle, 15 degree of the remaining data. So this is a comparison. And in the 45 degree, it looks looks it improved the resolution along the z-axis, and this is a 60-degree missing and very largely improved. So the structure was difficult to see the real detail of the phosphate in the nucleic acid. And after the training becomes very clear to see. And on the 15-degree case, original is very bad, really bad. After correction is kind of help a little bit, not too much. So that means we have a limitation of this algorithm. So the limitation of the algorithm kind of kind of becomes a 15-degree of missing cone. So if you have a missing cone that better than 15 degrees, this algorithm should work as good as this, as good as the ribosome case. And this is another data set with beta galactosidase. And if you we do the 2D classification, the 2D classification and do the reconstruction, and this has we pick the side view, 1,500 side views, and another case we pick 950 top views. And we can do the independently to do the side view reconstruction, and this is independent to the top view reconstruction. And in the uncorrected map, although it still has some detail, but the feature are elongated on this kind of y-axis. And after correction, the density become more clear and continuous. So this is the improvement of the continuity of the density. And this is also the same. So the elongation will be removed after the anisotropy correction. And this is the next one is a misalignment correction. Because sometimes if you have a very strong peripheral orientation, it is very difficult to align the particle. You get a completely wrong alignment. So it completely wrong reconstruction. So this is a misalignment correction. It takes a particle set and probably want to give it a reference, which is typical OK reference, without this artifact reference, and then go through this step. For each step, you do a alignment you rely on, and then do the post-filtering like filtering, and then insert the anisotropy correction in between the alignment process. So the training network actually happens here, and then do the low pass filters for resolution cutoff, and go the iteration by iteration by iteration. This is only implement in Reline, and if you want to use it, you need to remove the blush regularization, because blush regularization and anisotropy correction actually occurs in the all of the take over the external reconstruction in the Reline. And if your particle cannot align at all, so you probably want to use a keep low resolution, the argument. So it keeps the resolution as the low resolution inside in the structure and for the reliable alignment initially. So the reconstruction will not diverge in the low resolution scheme. So they will still keep the similar shape, which is very important. The low resolution information actually keeps the particle without searching for all the possible location and give you a worse structure. So this module actually implemented as a plugin in the Reline, just type the external reconstruct, and the Reline will look for the external reconstruction module and run the spIsoNet during the Reline refinement process. So the alignment and network training, network training. So after that, go through that, it gives you a better alignment of the particle data set. So this is another test data set. So this is a tilted data set for the HA, which are influenza virus spike proteins. So this is a standard Reline refinement. So actually remember, this is a tilted data set. So that means the data set collected with a tilt, with 40-degree tilt. This is a Reline refinement. This is an isotropic question, which you can see it helps you to define the side chain. And this is a misalignment question. So after misalignment, the side chain become much more clear. So the arginine become the density appears here. So without side chain to the with some side chain. So this is the tilted data set of HA. And this is actually so if you see the 3D Fourier shell correlation, it has some missing information at the z-axis here and here, and after the question, it become almost spherical. The Fourier shell correction. So it's if you do the 3D Fourier shell occupancy, you call it 3D FSO, you can see an anisotropy range reduces. So by the way, so this one is only for the misalignment question. So all the map is directly reconstructed by reline. It's not neural network modulated. This is from original particle and reconstruct with reline and from the missing alignment fraction. So it's kind of they use the same particle, same reconstruction algorithm. Only difference is the alignment of the particle. This is another case. It's very extreme. So it does not have side view at all. You can see the triangular shape of the particles along the on the ice. It's very hard to see any side view. So this is also the spike protein of the influenza virus, and if you do the standard reline reconstruction, it becomes a very short structure. So with the very short structure, we probably need to rely on the realign of all the particles. So with a misalignment question, this is a reline process of misalignment question, and this one is a misalignment and the structure question. So the structure, the detail appears after you have a good alignment and have good alignment, and also with a neural network modulated the density. This is an extreme case, and you can see the density actually improve a lot. Side chain actually also very prominent, so can define those very small details, the glycan on the structures. And in addition to a single particle analysis, this is also useful for subtotal averaging. And because we have a denoising embedded here and make it more isotropic, and we believe there will be a use case for also subtotal averaging, because this one can also help the alignment of subtotal averaging. So we try with HIV data set. HIV is the GAG protein we saw before. It's the same data. We the five tomogram and pick the particle as standard. And this is the standard subtotal refinement. It looks nice, but after the misalignment pressure, the detail become more prominent. The structure is here and well better defined compared to the standard reline. So it improves the resolution because of we have an isotropic map, we have a denoised reference for the subtotal averaging. So you can prove that the better denoising in between the alignment helps the subtotal averaging. So this is just published in a few months ago, and this is the summary. We have the self-supervised learning. So everything learned from the only observed data. So only from tomogram or your structure. And using the fact that true signal distribution is invariant to the rotation and translation, because you rotate it and you can also, so that means if you have a structure and if you rotate it, cannot it's still the same signals distribution. So it cannot recognize which is X, which is Y, and which is Y in the real ground truth. And the second one is isoNet for the missing wedge to help the molecular sociology interpretation in the cellular cryo-ET, and single party isoNet and compensated computationally instead of other physical and chemical treatment of the grid. And we have a, so this is the thank you slide. So thank you for listening. And we have a GitHub, the isoNet cryo-ET have both software are in the same GitHub account. And I'm working at the California Nanosystem Institute as a postdoc for more than 5 years. And it was my supervisor, Hongzhou, UCLA. And Hong Chengfan is a person that helped with a single particle isoNet, but have a lot of tasks. And Wang Hui helps to divide the GUI for the isoNet. And also our collaborator, the Zhang Heng, and which was who is undergrad and during the isoNet publication, and also the professor Guo Qiang with collaboration to develop the software. And thank you all for the listening. So I'm happy to take any questions.
All right, thank you. Very, very cool work. So we have some questions in the chat already. So first question is from Guobin. Very impressive tool. Do you think there is any limitations?
Yes, there are some limitation because this one is data driven. So how it perform kind of rely on how good is your data. If your data is perfect aligned, so the Q series is perfect line, and the noise is just no noise, I have good 60 to 60 degree of missing wedge defined. So this will be recovers everything. And if your data set is kind of not perfect, for example here, so we can have, so this is a single particle isoNet because with that we can have a ground truth. Okay, so we have if I have a 16 degree of missing cone, and the recovery is not very good. So that means to have a limitation that should be around the 15 to 13 degree of missing cone, and that one is a cutoff. If you missing information more than that, the isoNet will not do anything to you. So there's a limitation because of the data driven problem. But in general, it will help a little bit. Even helps in the tomograph. And if it's very bad tomogram, and it will not cause artifact, not added additional information, because this one was designed not to add more information, so it become more trustworthy. So this is that.
Okay, second question is, how does isoNet perform on tomograms taken from the carbon/graphene as opposed to from a hole? Can the automatic masking be turned off or modified?
Oh yeah, so if you see that, so the mask is they have a mask. So if you have a carbon graphene, so I have an automatic mask generation. If you don't like it, you can take the mask out and use your volume eraser to erase anything on the mask, and then you can use it to load it. So have a if you scroll here, you can actually give your own give the mask to input the mask here, and then you can use your own mask for the training. So if the carbon typically doesn't affect a lot, and also but it's still very good to remove the carbon region, and you can also turn off it. This is fine. You can also turn off, and also can draw a polygon to define the mask area. So this is a feature that implementing isoNet can draw a polygon in the 3D model. Have a tutorial about that. Have a 3D model to define the region you want. And yes, so this one is you can provide your own mask, And also also there's another option called Z-axis crop, can crop along the Z-axis. So there are a lot of options can try for the masking. So we actually think a lot about the masking.
Okay, next question is how many particles are ideally needed for challenging samples and without the use of reference maps? This is unlike the beta gal.
Unless the beta gap. So how many? So it's not the particle that matters. It is the structure is matters. So the structure. The so if the reference map is typically not necessary if your refined structure is roughly the correct shape. For example, here you don't typically need it. From here you don't need it because the strip is kind of correct. From here you from let's see from here you can either you can use a reference map or you don't use it. So because this can do either reference with reference or without reference. This is also fine. So this is for this is should be okay without the reference map. And if you really encounter a problem like this, like you cannot get a structure at all, it's completely wrong. So this is a case you want to use the reference map. Okay, this is a key. So if your structure is not good at all, you probably want to tilt it to create a very small set of duty sample, and then or just maybe just 20 degrees of tilt. Just make it a structure roughly correct, and then this should be fine for the FP isoNet training. So it's not the so that means it's not the particle needed. So it's actually the structure itself. But whether you have a very severe preferentiation or have mild preferentiation. If it's severe preferentiation, you need to do some reference. Yeah.
Okay, does anybody maybe have one more question for Yuntao before we move on to the next speaker?
Yuntao, thank you for such a great talk. I have two questions. The first one is really amazing to see the comparison of the tomogram from IMOD or from isoNet. So then I'm wondering if you just do the denoising without doing the filling of the missing wedge information, how will that change? Since here, for example, on this slide, so you're not near the equator, loss region, we can see this information from the IMOD part. But on the right-hand side, so you can see it much clearer. So I'm wondering if you just use the denoising, will the light region, will loss region be similar? So just like the bicycle,
Yeah.
two sides are much better than the top and bottom.
Yes, you can definitely do without denoising, but typically denoising helps to visualize. So if you don't do denoising, you still can recover the information, but with the denoising, the structure looks better actually. So if you don't do denoising, it still can recover, but not as good as with denoising.
So my question is really if we don't do the filling of the missing wedge information, just do denoising, then how will that look?
How will that look? For yeah, so there should be denoising effect because isoNet doesn't implement standalone denoising. So this is what this I haven't tested before, but you can imagine it should be similar with what something like Croquet or Topaz denoise or WAP. So they already have the noise to noise denoising. They should be similar to those kind of applications. So it still has the missing wedge. still very, very strong missing wedge, but its noise is mostly gone.
Okay, thank you. So the other question is about you showed the how much information we can miss, the 30 degree, 15 degree, 45 degree lows. I'm wondering in those investigations whether all others informations are completely removed or some of the information is still included.
So for that simulated task, because we can only do that in the simulation, otherwise cannot get
Yes.
tools. This is completely removal of the information. So let me get it, show the slides. So where is it? So I
Yes.
think this is this. So this one is a missing cone. This is a missing cone. So for example, this 15 degree, so only keep the information in the Fourier space, only those small cones. Other places are just completely removed. There's zero out other place. They just literally put zero on these pixels, and then we do the simulation. So it's completely missing.